reversible, adiabatic, one-dimensional flow, of an ideal gas through a nozzle. A nozzle or diffuser with both a converging and diverging section is shown in this picture. The minimum cross-section area is called truth. Our first consideration concerns the condition that determine whether a nozzle or diffuser should be converging or diverging, and the condition that prevail at the truth. For the control volume shown in the following relation can be write this control volume. We can write the first law say that property relation TDS DH dP on rho continuity equation rho AB equals to constant d rho on rho Combining these equations, we can obtain the relation dH or dV dP. Substituting to the last equation, dp, which is also equals to since the flow is isentropic, dp on 0 v square n square, and therefore dA on A dP on rho v square Mach square. This is a very significant equation. For from it we can draw the following conclusion about the proper shape for the nozzle and diffuser. For a nozzle dP is smaller than 0, with considering this relation. For a subsonic nozzle, we can write this relation. For subsonic, it means that n smaller than 1. So we have dA on A greater than 0, dA greater than A. Excuse me, dA on smaller than 0, dA, because A positive, nozzle is converging. For a diffuser supersonic, nozzle M dA nozzle is diverging. When M, consider this equation again, dA on A dP on rho v square. When M equals to 0, dA equals to M equals to 1, dA equals to 0, which means that sonic velocity can be achieved only at the truth of a nozzle or diffuser. We will now develop a number of relations between the actual properties, stagnation properties as the Mach number. These relations are very useful dealing with the isentropic flow of the ideal gas in nozzle. The equation available for the first law say that for the stagnation point, H0 V2 to Cp0 T0 minus T for ideal gas, since C square two and V2 on C2 or we can write this relation T0 on T for the stagnation point, for an isentropic process we have therefore P0 on P M square rho 0 on rho M square critical pressure temperature for the isentropic flow of ideal gas with the values K, value of P on P0 or rho on 0 and T on R given as a function of M in table A12. as a function rho 0 on rho p 0 on p and t 0 on t, table L12 as a function of m. The condition at the truth of the nozzle can be found by noting that m equals to 1 at the truth. The properties at the truth are denoted by the asterisk. Star. So we can write T star on T0 P star on P0 rho star on rho 0. These properties are the truth of nozzle when m equals to frequency refer to critical pressure, critical temperature, and critical density. P star pressure, rho star critical density, P star, rho star, and T star critical temperature. They are also tabulated in table 17 1 in the chapter. The next section is mass rate of flow of an ideal gas through an isotropic nozzle.